Hello everyone. In this video, I would like to discuss a very nice generalization of the classical Thales theorem. In the original version, the Thales theorem states that if a triangle is right angled, then its hypotenuse is the diameter of a circle. So in other way to say the statement is that if we fix B and move AC around the circle, then AOC is always concurrent, which means AC is the diameter. This is really classic. But if we generalize the circle into ellipse, so what will happen? So let's do a couple of experiments. First, we want to do the same thing. We fix B and move AC, right? Still keep ABC as a right angle. So in the circular case, the incidence is very boring. It's just the center. But in the generalized case, you can see if we fix the right angle here and increase the number of triangle, or equivalently speaking, we find a family of right triangle that inscribed in this ellipse and with its right angled vertex sitting at a fixed point. You can see that all these hypotenuse concurrent, which means this point is something like the center in the circular case, but this point is no longer the center of the outer ellipse anymore. Okay, the second observation is that if we change the location, the right angled vertex, in the circular case, it's quite trivial because the incidence is in the center. So no matter how you change the location of B, this point is fixed. But in our case, you can see the point of incidence is not fixed, but its trajectory is fixed. So this is the second interesting observation. And the third one, we can see that as the point outside travels in counterclockwise, the point inside travels clockwise. So we have opposite motion on the inner and outer ellipses. This is very interesting. The fourth observation, which I did not list here, is that if you change the eccentricity of the outer ellipse, the inner one changes as well. But if you take a look at the shape of this inside one and outside one, it looks like a smaller version of the outside one. Yes, this is actually a correct statement because the inner one is similar to the outer one, which means they have the same eccentricity. But the size of the inner one is kind of a shrinkage of the outside one by a fact of e squared over 2 minus e squared. E is the eccentricity. Okay, in the last part of this video, I would like to quickly explain how the code works behind this demonstration. And you can download the code from this URL. So in this code, let's take a look at the variables. The first one is the shrinkage, or the shrinkage factor I was talking about. It's e squared over 2 minus e squared, which is the e is the eccentricity. And x0, y0 is the location of these right angle vertices, which is specified in this way. And we also have a parametric plot. So this determines the inner and outer ellipse in our case. And the key step here is this part. If you play with the demonstration, you can see that it runs really smoothly and the right triangle spreads out evenly. So this is because the parameters I choose to generate these right-angled triangles given a fixed point is this guy. So this is associated with the slope of this hypotenuse. So if you use the k as a parameter and solve for the vertices in terms of k, you will have very nice closed form for the two endpoints on the given hypotenuse in this way. So this is one of them, and this is the other point. After the hypotenuse and ellipse are done, the leftover point that I need to add is the incidence. So once I figured out the math, the incidence is very simple. It is shrink, that's the shrinkage factor, times cosine theta and times this part. But it's not enough. We have to put a minus sign here because the inner one travels in the opposite direction as the outer one. Recall that the sine function is indeed an odd function. So the minus sign here is actually from the sine minus sine theta. But the cosine function is an even function. So cosine minus theta equal to cosine theta. So there is really no extra minus sign will be needed for this term. Okay, so this is all the key points to understand the code behind it. Thanks for listening.